们有个同学很希望看我们有没有同学有兴趣做。知道？对啊。
我感觉看起来那个没有到非常困难。我那时候有听那个图书馆长王老师他有讲，他有讲说，大概我们就是买一个类似这样 Robot 的东西，这样就好。我们大概要负责地方就这样。我感觉起来应该不会到太麻烦。
就看有没有同学有兴趣做，拉一下这个肉包。
到时候我应该会找这个区块链那边的人。因为我从区块链那边比较闲。对，应该这样。然后他是说大概6、7月就要开始动。
真的，看一的是兽医的，或者新生术理，新生物的那种师傅。
好像是，我记得可能可能那个学期一结束之后才开始，所以我觉得应该不会早出。刚好下载新的新款是那个。
哦，学校好。
应该不知道会不会找到，不知道。今天那个原来的那个微信群的，在，不是那个 DFS。
是 distributed file system 还是
DFS 啊？原来 DFS 对。
哦
两个都不在。
哦。distributed file system。
把 DFS 两个都把它打开。
好。是。OK。对。对啊，那每次这个会断掉怎么办啊？对啊，
这还真不知道有什么解法，要不然就这样跳。
怎么样？
没有，然后这个 Google Meet 每次开一开，它就自己断掉了。
哇，你就是每1个小时换一个，那现在怎么1个小时？
没有，
可是因为学校
没有。
对，学校
是可以的，但是它好像是自动会断掉。是，
它这个你就要下课再来开。
学校不，他这个他现在可能设定就是这样子的，你要跟学校反映啊，就是为什么会这样的，对，也就是说学校那边的说明可能是错的。
哦，好，
你要跟学校反映的。对，说我们上课上完1个小时，它就会断掉。那就叫学校去跟 Google 去确认了，到底是什么原因啊
？OK， 对啊，我看。我把它这样，但是我不要按这个。好，老师那时候是先上到哪里
？OBS 开了。
没有 ，OBS 开了。
我们是上到哪里？所以，应该特别。这 simple 的那个方式，再退回去。
simple 方式。
再上去。这前面。这个对，应该是在这里。
OK。然后那另外一个我再开在这边。它为什么不能显示？
就 synchronization，
对，这个。好。
Okay. Last week I think we stopped here, something somewhere around here. Okay. We're talking about stateless and stateful service, and we use this file access API as an example, okay, to say some discuss difference and the pro and cons of these two kind of design. Okay. In this lecture, we will continue our discussion about this file distributed file system. And first, we will give some example about this typical or the traditional simple file service architecture. Okay. In the past, the distributed file system usually has these three modules. Client module will be running in a client host. And server computer usually has two modules. One is directory service, another one is, we call it flat file service. Okay. The direct service may be implemented as a client of this flat file service. And the directory service is used to handle these directory related functionalities. And flat file service take care about this detailed file access. Okay. We will see some of the API examples. Okay. So the component for this is for flat file service handle this access to the real file content, and usually they use a globally unique identifier, okay, to access these files. Okay. So this usually they use the low-level file identification. And the directory service provides a mapping between the user readable text name of a file to layer unique file identifiers. So the functionality for directory service will be something like create a new directory, add a file name to a directory, and obtain file ID from their parent directory, and so on. In most cases, they are implemented as a client of this flat file service. So the content of the directory, or sometimes we call it directory files, they are also stored in the flat file service. Okay. That's if they implement it as a client of this flat file service, then the directory files will also be handled by this flat file service. Okay. But of course, you can implement in different way. You can implement this service as its own, okay, without using this flat file service as to handle these files. Okay. But most systems they use this approach. And the client module run in each client computer. Integrate and sometimes they extend a local native file system or provide. Usually, most modern systems they use a virtual file system layer, so the mapping in that layer will translate the access to either client module to the remote file service or to layer native file system API module to access local files. Okay. And this kind of module they can access this flat file service and directory services. Okay. In most implementation, they may implement this client module in user level instead of kernel level. Okay. So the API for flat file service usually has this simple semantic. For example, you may have a create used to create a new file, okay, and return a unique ID, okay, and read because most of the API for file system use this stateless. This is a stateless API. Okay, so you give a file ID and with the starting point, okay, and the number of items. Okay, so this I and A is the starting position. and N is the number of items. Okay, and then this output will be the related data. The right, okay, they use this the size of here. Okay, the size of this data is self-contained in this data. Okay, so they only need the starting position. Okay, and delete can be used to remove, physically remove this ID from the file store, or actually remove the whole file associated with this file ID. Okay. An attribute can be get attribute used to return a related file attribute, or sometimes we call metadata. Okay. And set attribute is used to update this attribute. Okay. So this free file service, their API usually is very simple, just is necessary operation related to access a file. Okay. And the directory service will be something like this. They use this directory name and file name. Okay. And here they will look up this directory to find this file and return this file's corresponding unique ID. Okay. And so you can use a name to add a name into a directory. So you add this name into this directory, and the ID of this name will be something like in here. Okay. And remove a name used to remove an entry from a directory. Okay. So, but you can see that this only remove the entry from the directory. It did not really delete the file, okay, from the file system. Okay. And this name sequence is used to find out multiple files in a directory. Okay, so usually you give a pattern. Most cases is a regular expression. Okay, then the directory service will look up this directory to find out all these names, component names. They match with this pattern and return a sequence of its name. File names, okay, in this directory. Okay. So all the file names they match with these patterns will be returned. So it's a list of names, okay, or we call it a name sequence. Okay. So this is the simple directory APIs for this directory service. Then after we have this understanding of what is the simple file structures, then we will discuss two very typical examples. One is this network file systems, NFS. Okay, in the past, this supported by the Sun Micro bankrupt or acquired by and so now this NFS belong the property of the Oracle. Okay, so they change the name, become Oracle NFS or Oracle ONC or whatever. Okay, but it's the same thing. Okay, and so we can see that in a client computer, their implementation usually in the beginning, these systems are supported by Unix on top of the Unix operating system. So all the Unix-like or Unix descendant operating system, they use this similar ways, okay, implemented. So they implement a virtual file system, and this virtual system will intercept the request for the file access. So and if the file is in the remote, then they will pass to the enterprise client. Otherwise, they pass to other native other file systems. For example, if its native is Unix, then it will pass its Unix file system to access local files. If it is a remote, then another client will send a request using this NFS protocol to communicate with the corresponding servers. Okay, and again in server computer they also have this virtual file system implementation. So this NFS server will call this this layer of virtual file system, and then inside here they will go to this native Unix file system to find out the real files. Okay, so And here, because this virtual file system, if the file is in this local disk of this server, then that would be something like this. Okay. If the file, because the mounting of this in the file server, maybe mount the other server's file as well. Okay, so it's possible this NFS server go up and then go down to another NFS client in this NFS server, and then send a request to other file servers as well. Okay, so it's possible. Okay, that's why this virtual file system layer can be is implemented. You can accept the request from NFS server or request from application. Okay, and then they will translate this file mapping to either its local disk or a remote service. Okay, so the remote service means they will use an NFS client module to communicate with those remote files. Okay, and here we will give some example, a subset of these APIs in NFS protocol. Okay, and then we will understand what the relationship of this and this simple file system architecture. Okay, so in this subset, we contain some directory service functionality and some of the free file service interfaces. Okay, so this, for example, this lookup is a directory service interface, but in here, the lookup it gives the directory file handler. In NFS, this UFID, they are replaced by this file handler. Okay, that's a data structure used to contain the information about the file, the physical location of the files. Okay, and with the file name, and then it will return a file handler for this particular files. Okay, with its attribute. It's like a lookup in the directory service. The create will be used to create an entry, this file name, in this directory, okay, with original attribute. Okay. And also, they will return the file handler of this particular files also, with new corresponding attributes. Okay. If the attribute after this creation, well, some of the attributes are modified, then the new attribute will be returned. Okay. Remove, that means you remove an entry from this directory. Okay, okay. So this API, they all use file handler, okay, instead of the name, okay, for this to access this file. So here, the directory is itself a file also, okay, and file is also a file. Okay, so they all use the corresponding directory handler. Okay, and here the directory create the role of the unique file identifier. Okay, and get the attribute, set the attribute, read, that means you read access for real files with this starting point and the number of bytes. Okay, because in NFS they use a byte sequence, so every each item is a byte. Okay. And write is similar, okay, so but with the data. Okay. Rename, that means you can change the file name to another. Okay. And in here, the rename is much general. Okay, you actually contain two kinds of semantic. One is that you rename the name in the same directory, but another possibility is you move a name of entry from directory to another directory. Okay, so during this moving, the name can be changed as well. Okay, so you can use in both ways. Okay. The two is two directory is same as the direct. Then is rename the normal sense of the domain. Okay, but if this is the different directory, then that means it's a move. You move a file from this directory to another directory. And in the meantime, you may change the name as well. Okay, so you can do by this or by this rename API. Link, that means you create a new file entry with a new name, but link to the same existing file. Okay? So this new name may be created in another directory, and they will link to original existing file, okay, in this directory with this file name. Okay? So it's like in Linux, in Unix or Linux, you use the link, create a link, a similar way to do that. Okay? But the difference in here, the link and symbol link are different. Okay, link means these two file name. Okay, after this link, they all map to these new names, also map to the same file handler. Okay, as this original name. Okay, but if instead of so to implement this, usually every file, real physical file, will contain a counter, a link number to recall how many these links associated with this particular physical files. Okay. But another kind of link is symbolic link. Okay, so they have a different API for the symbolic. That means they create a new name in this new directory. Okay, and this string is the value, okay, stored in this spatial symbolic link file. In general, this string is a path name of this corresponding files. Okay, so you create a link, okay, an entry in this directory with this name, okay, as this file name. Okay, but inside the file, instead of map to a real file, this file only contains a path name of the corresponding files. Okay, so you use this. So when you open the file, which is a symbolic link, you really try to open this file, okay, instead of original file. Okay. So the implementation for this is that. But the reason for doing this is that, okay, now you don't create a real link, so the counter of the original file, physical file, will not be increased. Okay. So this symbol link will not affect the counter of the real files, because it's like you only recall a particular file name inside this spatial symbolic link. Okay. The reason to doing this is that now if the corresponding file has been deleted, then this access will generate an error. Okay, because the symbolic link did not know. They can only find out the facts when you try to open the file corresponding to this symbolic link. Okay. Then the open will fail because the file is not existing. Okay. So the delete, remove of whatever of the original file will not affect this setting. Okay. And also remove this one will not affect the setting of the physical file also. Okay. So relink, that means you read this string, okay, corresponding file description. Okay. You read the link of this particular file, okay, and return its path name. Okay. Method is it similar to create a directory, but create a new directory under this original directory. Okay, so it's a Mac directory. Remove, that means instead of remove a file, you remove a directory, subdirectory from the directory. Okay. Redirectory, that means you read the whole entry of this directory, okay, starting from spatial count, return up to. In here, this count means the number of bytes from the directory entries. And each entry may contain a file name and corresponding file handler and a cookie to point to the next directory entry. Okay. So this is the NFS port. And then they will return the number of entries corresponding to this count. The last one is file system statistic. Okay, that means it return the file system's information, okay, of this directory. Okay. Okay. In NFS, to access remote file, before you can access use the NFS protocol, they have another protocol called mount protocol. You can use this mount protocol to attach a remote subdirectory into your local file directory hierarchy. Okay, so something like this. So, for example, this is a client machine. Okay, these are its original setting for its local directory. Okay, and in this example, there are two file servers, server 1 and server 2. Okay, and in server 1, they export this directory. So all the corresponding client host, they can attach this subdirectory into its local hierarchy. Okay, so in this setting, this client machine attach these people, this subdirectory into students subdirectory under this /root /usr/students. Okay, and also they attach this /usr staff to this directory. Okay, /nfs/users of the server tools. Okay, so the file system of the client mount this, okay, from server 1 and also mount this from server 2, and then to make construct its file hierarchy in this client machine. Okay. So after this mounted successful, then you can use the NFS. You can use this local file structure. Use normal file access API to access these files. But during this access, when you access a component or file inside this student's subdirectory, the virtual file system will automatically translate calling this NFS client, and will send a corresponding request to this particular server. Okay, and if you access a file in this step subdirectory, then the BFS will transfer to calling the client module or client, NFS client, okay, in this client host, and then the request will be sent to this server 2. So that's how this NFS works. Okay. Here we will discuss some more detail of how this page name, because of file contain a page name in a local file directory, right? So how they transfer this page name into file ID or whatever. Okay. This page name are not translated as server, okay? Because remember, in the past, NFS before version 3, they are stateless protocol. That means server did not keep any information about client. So all those necessary information are kept in client. Okay. So this page name translation or lookup implementation is implemented mostly in client. Okay. Of course, server will need to support functionality of the lookup, but kept this component translation need to be done by the client, okay? but one component at a time. Okay, so they are not translated. So you are not pass a whole page name to the server. Okay, you pass the component name. Use the lookup interface here. You use this lookup one component at a time. Okay, and after the lookup, they will return the file directory, file handler, and then use this handler to look up the next component and so on. And those translation or those file name resolution, the result of those resolution will be maintained by the client host also. Okay, because the server did not record any state information of client's request. Okay. So that's the basic idea. And the name, the whole page name may close several mounting points at a time. So directory hold different part of a multi-part name, maybe in different servers. Okay? So they translate it in an iterative manner by the client. So one component at a time. Okay? And whenever they get a result for a particular component, then those components will be kept or caged in the client host. Okay? Because remember, for most file access patterns, if an application running in a particular client host, those files needed for this application, usually they will reside in same directory, okay, in some sense, or very closely directory, or at least in the same hierarchy, same directory hierarchy. Okay, they may have the same parent of directory and so on. Okay, so those previous lookup result may be useful for the subsequent file access, okay, for the same applications. That's why this lookup result will be kept as a cache in the client host. Okay, when you execute in an application, you open file 1, and later you maybe try to open the file 2. This file 1 and the file 2 usually they have somehow closely related. So they may in the same directory, or their parent may in the same directory. And so this lookup operations for the file 1, those components may be still useful because the directory structure usually did not change very often. Okay, at least during an application's life cycle, usually those related files, their hierarchy, in most cases that they will not be changed. So those lookup cache the result of this lookup is still useful when you try to open the second file. Okay, then you only starting lookup from those different parts. Okay, those the page name in the beginning of the page name, they may all be the same. Okay, so when you look up the first file, you go through those operations and record results. So when you try to look up the second file, if the second file has the same directory or same parent directory, that's the first file, then a lot of this translation will be omitted by using this cache. Okay, so caching the result of each step can make this iterative lookup become much efficient. Okay. In the implementation of this interface, okay, server side, they also may use some kind of caching to provide better performance. Okay, most implementation of interfaces they support both read and write operations for the cache. For read, they use a read ahead caching. Okay, so you can read some of the unreaded pages or blocks. Okay, for the subsequent, they will anticipate because the access usually is sequential access. Okay, so when you try to get a block of a file, a particular file, then the file system, file server, they may automatically cache or preload some subsequent blocks from the disk to move the disk to the content from the disk to server's memory. Okay, so this is we call read ahead caches in the server memory. Okay, and in the write operation, okay, they use some form of delayed write cache. So they allocate some memory in server. So the write only go to the server's memory until later they will flash to the disk. Okay. So this direct write can reduce the turnaround time for updates. Okay. They try to optimize write holding the update in the server cache as long as possible. Okay. But because this some of the data may be, if the server crashed, then some data they did not flash to the disk may get lost. Okay, so to support the data write, okay, and with some photon requirement, then this this memory, okay, maybe need to be special memory. Okay, for most current current machines, okay, computer machines, they have three kind of memory. One is main memory, okay, and then they may have a very we call it silicon disk memory. Okay, they use silicon disk as some kind of a temporary memory to hold in these buffers. Okay, actually it's a flash. It's similar to the flash memory. Okay, but they are putting in the inside the computers. Okay, instead of use as extended storage. Okay, but inside the computer as a cache buffers. Okay, so because this silicon disk, they are much faster than normal magnetic disk, okay, hard drive, okay. So you can save some time, okay. So this delayed write buffers, they usually maintain it in there, okay. And because this silicon disk, they are much faster than magnetic hard drive. So you can get some performance gain by writing to layer, and then you get a quick response back to the client. Okay, and periodically those contents in this silicon disk or flash memory, then they will store back to the disk. Okay, and so on. Okay. So to minimize this the possibility for this server crash. Because the silicon disk, they can tolerate machine crash, okay, as well. And in this NFS version 3 protocol, okay, the write operation, they support two kind of options from the client side point of view. Okay, so the client module, they may use write through cache or committed write cache. Okay. The data, the written data or updated data may be held in client's cache memory before. This is in the server side, not client side. Okay, the client side is in the server side. Okay, so even the delayed write, they support these two kind of mechanism. Okay. Write through cache means the data stored in memory, okay, and written to the disk before the reply. This is same as the original one without this delayed write. Okay, they just write to the disk, and also kept one version in the memory, okay, as well. Okay. The reason kept this version in the memory is that for subsequent read, then for the same block it will be faster. Okay. And second one is we call committed write cache. Okay. So data stored in memory and then written to the disk when a committed operation is received. Okay. And this committed operation can be sent from the client periodically or enforced for some time. Okay. Depends on the application. Okay. If the application asks for more reliable requirement, then they can send this commit operation. Okay. The standard NFS client, okay, they use this second option. They use this one. Okay, so they may issue commit operation when they open for write, and the write is closed. So before
close a file, their operation will be kept in the memory. Okay, so when finally the file closed, then all the write updated blocks will be stored back to the server. Okay, so this will reduce actual write operation to the disk, to the file server. Okay, to server sticks. But because the server support both kind of caching, and standard client use this one. Okay, that means if you try to use this one, then you need to implement your own client, or you configure your client module. Okay, when you run your client module, you can change the option to this one if you like. This option will be used. Okay. And also in interface, the client also use doing some cache. For example, this lookup and read write, they're all doing caches. Okay, because it is a stateless protocol most of the time. So to make the operation much efficient, client should cache some of the previous result. So later, if they try to access the same part of the file, then they don't need to go to the server again. Okay. And because this, you need to have a way to validate your cache is the latest version. Okay, so to avoid this data inconsistent, okay, the write by a client, they may not reflect to the other client as well. Okay, immediately, because your write only go to here, committed write, you don't go to the memory. Okay. And also, you use the client-side cache, so some of the write made in your client-side as well. Okay. So that become the client's responsibility to poll the server to check its cache is still ready or not. Okay. And to enforce this validation, or to make this validation become much easy. So remember here, okay, so this is a client-initiated cache update policy, okay, because it's a stateless protocol. So most of this checking must be initiated by the client, and the timestamp usually used to validate cache block. Okay. Here in NFS, each data or metadata and attribute, okay, they may be cached. Okay, they have two timestamp. One is in cache entry. Another one is corresponding to the server's timestamp. Okay, so every client they will maintain these two. Okay, this is the last validate timestamp for a particular cache line, cache entry. Okay, and also for that particular cache block, you also maintain the last modified timestamp from the servers. Okay, and whenever you try to access a cache entry in your client memory, they use this following rule to validate. Okay, so for example, this access time is t. In time t you try to access a cache. If t minus tc is last validated time, okay, is less than the predefined interval. Okay, this interval usually called freshness interval. Okay, if this time is small enough, then you assume that the cache is still valid. Okay, the assumption is you make some assumption in here. Okay, or okay, if this is the case, then you use this cache. Or if it's not the case, then you try to use another rule. Okay, if the TM record in the client match the TM at the server. Okay, so of course to validate this you need to send a request to the server, okay? That's why we these two rules in this order. So you first check this rule. If it's good, then you use it. If this is not good, then you try to validate this one by sending a request to server, okay, to see you recorded the last modified timestamp is same as the server's recorded timestamp. If it's the same, then that means your cache is still valid, okay? Okay, so doing this, okay. Of course, by sending this, you may cause generate a lot of traffic, okay. So most of the time, most systems use this piggyback mechanism, okay, to minimize this requirement for this modified timestamp, okay, to validate this, okay. So they use this get attribute operation to obtain the timestamp in the server, from the server, okay. So when it needed, you try to validate a particular cache line, you send a get attribute operation to the server and get back this timestamp of the servers, okay. However, you will not try send a get attribute only for that particular block. You will send a get attribute for all the block you cached in one message request. So the server will return a lot of timestamp associated with those blocks. So you use one get attribute operation to get back all the cache line in your client and get those timestamp back, and then you update your timestamps. Okay, if those timestamps they are matched. Okay, if they are not matched, then you invalidate those cache. Okay, by doing this, you save a lot of requests of this. So whenever you try to access a cache, and then you need to validate its cache line, its timestamp. Okay, you send a get attribute to the server, but instead of sending one for one particular block, you send get attribute for all the block cached in a client. Okay, so the server will return a set of timestamps for those blocks that's modified timestamp. And then after this return, you doing the validation. You some of the block their time this time are equal. Okay, then you those block is still valid. If some of the cache block their modified time is not equal to the server side, then you set those block become invalid. Okay, so then here comes okay. This then periodically, okay, you may get those blocks from the server for those invalidated blocks. Okay, it depends on how you do that. Okay, but most NFS they use a daemon process. They periodically they will send requests to get those invalidated block back from the server. Okay, it's all okay. So to reduce this call to server, that means whenever you receive a new value, you apply to all the cache entry for the file. Okay, and these values are piggyback for every operations. So this get attribute. Okay, whenever you send a request to the server for other purpose, you also associate this get attribute. Okay, so the return the value for the when the client communicate with the server for one particular operations. For example, you try to open a file or whatever. Okay, so when you send this request, you also piggyback this get attribute. So the return the message will contain your original desired result with piggyback timestamp of those block you want to validate. Okay? And then you validate those blocks whenever this piggyback information. Okay? That's all. Okay? So using this to reduce the number of this get attribute associated. And also, because this T freshness time interval depends on how much, what is the average time or the past history about this time should be defined. Because if the file is a directory, then usually this time may be set longer, because in general, you will not update the directory content very too often. Okay? But the file in general is much frequently updated than a directory file. So in most cases, a file usually you set the T to be 3 to 30 seconds, but for the up directory usually set to 30 to 60 seconds. Okay? But of course, this T is adjustable, depends on your collected history. Okay? Then you can dynamically change this freshness interval, okay? when it's needed. Okay? And also in client side, or a cache page may after whenever you update, you will mark as a 30, and then you will schedule this 30 block periodically to flash to the server. Okay. Of course, when the file closes, you need to be flashed. Okay. Or client issue a sync operation to the particular file. Okay. Or you enforce the flashness, the flash, then this page, 30 page also need to be written back to the server. Okay. And again, in server we implement this real ahead and delete write cache. In client also, if server side implement this, then client side can also support this also. Okay, read ahead and delete write. Another client they do something, do some asynchronous operation, rewrite, okay, by its own. Okay, and this usually implemented by using this bio demo. Okay, bio means block input output demo process. Okay, so whenever you launch an enterprise client in Unix or Linux, then they automatically launch this block input output demo process. Okay, so whenever you receive a reply for each request, okay, then this bio will automatically generate file access, read access to the server to read ahead to implement this read ahead operations. Okay, and also they will send back block, this dirty block to server. Okay, when if those blocks are newly created and they are full, okay, then they will be sent back to the server, okay, on behalf of this each client application. Okay, so by using this bio demo, okay, periodically and with this some event-driven operation. Okay, whenever you read something, you automatically generate some subsequent reads to the server, okay, to anticipate that in near future the client application may need those blocks. Okay, so you read ahead, and for the write, if you client create a new blocks for a particular file, then after this block filled, then they automatically flush a whole block to the server. Okay. That's for the normal files. But for the directory blocks, if the write block is associated to a directory file, then in general, every modification will be sent back to the server as soon as possible, because the modification for a directory usually require immediately be not viewable to all the clients, okay? Because you have a new file or a new file entry was deleted or whatever. Those situations need to be immediately captured by all the clients. Okay? So that's in general the case. Okay? The second example for this simple file system is we call it Android file system. It's 11 already? Okay, so let's take a new short break. Okay?
那个 Dance 那篇，那个数学老师说他那边可以投，可是要给他写。
给他写是哪一篇？
就是第二篇
OK
Dance 那边，然后第三篇也是他写。
OK， 对啊。
好，没问题。
你叫他把那个就把那个数学老师写嘛，他本来就是 first order 是吧？
对，他都是 first order。
那就不用改那些东西。
你要看
先把它
关掉，关掉，
又不见了。
对，那个关掉了。
对啊，
它自动关掉。
他自己关掉了。所以我跟你讲，他现在就是大概只能用1个小时而已。
要再开吗？
对，还是老师我们就不要再开了，然后我们下个礼拜就只用 Teams 去开线上 ，Microsoft Teams。
OK。
我到时候再给那个。
那你先问一下学校集中哈，这是怎么回事啊？
好，没问题。
是不是他们已经改变 policy 还是怎么样啊？我会让他知道这个事情，因为跟上面的说明是不一样的。
OK， 没问题，那我到这边去讲。那就现在就先不要开了，喏。
先还是要开啊，你再重开就好，重开就好了。然后通知他们说以后可能会通知。
好，没问题，到时候去通知。
所以如果就是他们没有来的，他就说上看录影的，就这样。
OK， 没问题。
你还是有录下来的，对。
有录。你修课也修很多了。
还可以。
那个市委有没有说他们那边那个 dance 练能给他投哪里？
还没有，目前还没讲。到时候再，因为我就先把档案转给他，然后后面把那 reviewer 的意见也转给他。
对。
因为我觉得那 reviewer 的意见最后一个那个有点就是很麻烦，因为他说要跟其他的模型去比较，这一点我觉得。
其他我已经看到其他模型。我们不是有比的，我们自己的那一篇，自己的这样，你要跟其他什么？
他意思讲的是像我们 Resonate 啊，或者是那种不同的 CNN 模型，应该这样讲，就可能 Vision Transformer 那种东西，我在想可能会是这样子。
哦，那当然啦，那是一定，问题是这个题目目前就我们在做嘛。对，那你要跟那么多去比，当然也可以啊，你就变成要把幸福的那个东西拿进来。
因为我就觉得这一块相对，因为要写的话，就是到时候要把幸福推回来写。
那太没有，那就让他写到幸福那边投的时候再讲。
因为我不知道幸福那边他投出去
没有啊，那边没有投，
还没投。不是，他现在在写。
他没有在写啊，就是他硕士论文他只是在整理他硕士论文而已。
没有，是老师说他连幸福那边也要投。
哦，对啊，那没有问题啊，就叫他投的时候他要注意啊，这两边的关系他自己把它拿捏好。
好，那到时候再去跟室友这种。
好了吗？
好。那个老师，你有想要看那个，就昨天去港务局那 PPT 吗？
可以啊，可以啊。
那我到时候转给你，然后
OK 好。有没有什么特别的？
其实我觉得还好。
还好，对啊，没
对，
有问题啊。
因为我觉得他们主要是 focus 在那种塞港的部分。对，但是我们就是
塞港。
塞港对，
就是他目的是要通水。
就是因为其实我们一台船从就是进港的时候，进港之前到进港这个过程，到在港内，然后再出港，这个过程中，他们要有谁要来帮忙，然后可以避免说就是有什么事情要做，
就 schedule 就对了。
对 schedule，然后他的是谁负责啊，然后像是什么，就是他们船在进港的时候要引水人、引水船这种东西啊，这种过程。然后就是他要通知谁，就是他们想要尽量避免说一艘船在外海待的时间太久，然后造成那种不必要的浪费资源，就那种石油，就是他们在运转的过程中，因为就是他们大概是他们想要避免就这种事情发生。然后因为像基隆港、苏澳港那些不算小的港口，但是他们港口就比较不会有塞港的问题。那就用那黄老师他提出的方法，就是会相对比较没有效益，就是他提升的效益不大，应该这样讲。然后像是高雄港的话，他们就是效益可能会提升的比较多，大概是这样。就是他们就想要避免就塞港情况的发生，然后会影响到那种对不必要的浪费，就是那种能源的浪费，然后环境的污染大概是这样。他们最主要是想要提升这种事情。对，然后我们就是我们要针对我们这一块，就我们要负责的地方就是要去通知那种这个在一艘船这样进港到出港之间所有人的通知来罗把的扣的去写这一块而已。
为什么会想要用来罗把通知？
因为他们一开始是认为说，那个大部分的人，就我们台湾人，大部分还是以赖为主。
我知道啊，问题是赖的通知，除非你把那个通知打开哈。可是你通知打开就会有当然你可以把某一个特定的群组的，它可以只开某一个群组吗？还是你打开的时候，它就所有的群组都可以？
可以针对某一个群组去打开。
OK， 那样就可以，那这样还好，不然的话只是，所以他必须要他自己设定成这样，或者你会受到干扰啊，对。
因为其实我们那时候他们在那港务局那边的人也是针对提出赖这个点也是有疑问。但是我觉得我们这个只是就是缓兵之计这种方法，就是后续我觉得他们应该也会改变东西。
他应该比较好的应该不是用 Line， 而是用他自己的一个 notification 的 app 就好了，自己写一个简单的，就是反正你这些相关的人就把那个 app 下载下来，对。
因为他们好像是，我记得那洪老师一开始是说因为他们的 app 已经开发完了，然后他们不想要在那个 app 上面再做更动，所以他们才想要用 Line Robot 这样子。对，这个问题，那个其他港务局的人也有提到，为什么不用其他的 app 就好？对，因为他们也是针对什么治安的问题上面也会去有所疑虑。大概是这样啊。然后明天我会跟黄主任开会，那我到时候可能再做个 PPT 或者是录个音，然后到时候再跟老师讲。
OK， 好。Okay, we are back. Next, we will discuss another simple file system. Okay, we call it Android file system. Okay, it's another implementation based on this simple file architecture. Okay. In this file system, they have a client module and server module also. But here they give client module a special name called Venus. The server module they call it Vice. Okay. And the difference between this AFS and NFS, the most significant difference is that in AFS, every client host they have
two namespace. One is local. Local. The namespace in the local means that this name hierarchy is only for a particular host. And the shared namespace for all the machines, they are all identical. Their namespace, their hierarchy are all identical. That means for those files, if you create a file, you need to be shared to someone. Then you should create in this shared namespace. Then the name of this file can be accessed from any client with the same file name, okay, same access method and so on. Okay, so that's a compromise of this file naming mechanism. Okay, for local files, their name can be different because the purpose for those files is not shared. Okay, it's just for particular user to use them for in the particular local machine. Okay, for those files, you may be shared. Okay, then you need to create in this shared namespace, and this shared namespace are all the hierarchy are identical in every client host. Okay, so you can use shared namespace in every client machine by the same way, by the same file name. Okay, so that's the design in this intro file system. Okay, and local file system for those files. Okay, this is system files, for example, min. Binary library or whatever, they are in the shared file also. Okay, but for some access pattern or fast access reason, okay, in each local machine, they usually create their local copy, and this local copy is a symbolic link to this shared binary. Okay, so usually for these binary system libraries, they have this symbolic links associated. But other than that, all the other files, if they are shared, then they will be created in the shared namespace. And ever also they use two mechanisms to achieve high scalability. The first one is whole file serving. That means they use upload download mechanism for file access. So whenever you try to access a remote file, this shared namespace, okay, they will download the whole file into your local cache, and then you use this local cache to access. So that's the whole file, and also whole file caching. Both. Okay, so you access the whole file, and also cache the whole file. Okay, that's way. And after FS version 3, okay, in the beginning it's a whole file because in the beginning the size of the file is not, in general, it's less than 64 or 1 megabyte or whatever. There's more, but after FS3 version 3, they find out larger file become very common. Okay, so they break this whole file serving into chunk, block. So every block is 64 bytes, okay, instead of whole file. Okay. And also the file caching, the whole file caching, is still used. Okay. So once you open the file, then the whole file will be cached in its local disk. And every disk may contain several hundred cached files. Okay, and this cache are permanent. Okay, as long as the storage size permitted, then they will kept there. Okay, the reason for that is that although the user can log in into any client host, but in general, most users they log into the same host. Okay, in the normal situations. Okay, so if you when the user log into a client 1 and then you run its application there, okay, next time the user most often they will also log into this client 1 and to run its application. So those catch the fire for a particular user is still ready for later uses. Okay, that's why. So as long as the cache directory, cache disk, the size of the cache disk is big enough, then they will always kept there. Okay. Of course, the cache file replacement need to be performed when the whole local cache are full. Okay. So whenever you try to open the file, if there's a local cache, then you use this local cache instead of the more servers. Okay. And the reason for this design strategy is that before they design and make this decision, they do some historical data analysis and then find out the maximum size and the located reference in the past. Okay, they usually find small, but most likely they are less than 10 kilobytes. Okay, in that time, okay, 19. Don't remember, 19 something, 79 or 78, okay, in there. Okay. And they also measure the operation frequency for read and write and find out that read operation is 6 times more than the write operation. Okay, so in this way, it makes sense. You catch the whole file, and they also make a decision when you close and update the file, then you move the whole file back to the server. Okay, and also sequential access is more common than random access. Okay, and also this is very interesting point. Most files, although they may share, in general they are written, especially written only by one user. Okay. Most of likely is the creator will be the only writer. The others, they in general only doing some read operation. Okay. And file usually are accessed in burst. That means if a file being referenced, then more likely it will be referenced in the near future. Okay. And so, because whenever you create a file, you try to use it. So then later, for some purpose, of the purpose of the file will still ready for the subsequent days, okay, or even weeks or months, until, for example, you close a project. Then those files may be sitting there. You will not access very often, okay. But during a project's life cycle, those files will be accessed very frequently or modified frequently. And so, okay. So that's the access. So based on this, so they make this decision, okay, because the file usually are not big enough, okay, so they do the whole file caching and so on. And here we discuss some operational scenario in here. Okay. When the user process try to access file, they use open call and to the shared file space, if the file is in a shared file space, okay. And if after the mapping, name find out it is not in the current cache, in the current local cache, then the client module will try to locate the server which contain the file, and then send a request to get a whole copy of the file. Okay. And after they get the whole copy, the file, then they will cache in its local cache directory. And then the local file will be opened by normal Unix operation. And then user will use this local file, okay, for subsequent access until closed. Okay. So when it closed, and then the Venus, okay, this client module will check if the file has been updated or not. If it update, then we'll send back the content with a timestamp back to the server. If the copy is still maintained in the client, okay, for future possible access, okay. And if not, if the file is not updated, then you don't do anything in the closed. Okay. So basic concept for this is that they have two modules. Okay, Vice is a server software, Venus is a client. Okay, and Fire are available either in local namespace or shared namespace. Local file, they are handled by normal Unix file system. Okay. And those cached file, usually they are cached in this stage temp, okay, for those cached files. So here is the system call interception in this client. Okay. So user, when trying to open the file, okay, and this request go to the Unix kernel, and Unix kernel will find out, okay, this is to a shared namespace, so they will pass this request to client module Venus, and then Venus try to locate that particular file. Okay, before that, of course, the Venus will check. Because Venus maintains its own mapping table about a shared file and local cache, okay? Because local cache is a local file name, okay? And shared file namespace has a unique shared name. Okay? So this mapping are maintained by the Venus for each client machine, okay? They maintain their local cache and corresponding shared namespace files, okay? And this. So when you try to open the file and then find out it's in the shared namespace, they will pass this Unix kernel will intercept. They will pass this request to Venus. Then Venus will doing this mapping to find out, okay, this shared namespace file is there's a local cache or not. If there's a local cache, then they'll open that one, okay, or pass the local cache to file name back to the Unix open system call, and then this during the Unix open system call, they open this local file, and so on. Okay. So that's cool. Okay. So in Unix, in each kernel, Unix kernel, each client and server, they're doing some modification. Okay, especially the first in the beginning, they implement using this BSD Unix, and then modify. To incorporate this client Venus and Vice. Okay. So open, close, and some other file system calls, they are intercepted and passed to Venus when they refer to this shared namespace shared file. Okay. And Venus will manage this local cache. Okay. And they may remove, they do the cache replacement and so on. Okay. And every file and directory in shared space have unique ID. It's 96-bit. Okay, so it's a very long number. Okay, and they partition this into three parts. One is volume number for 32-bit, and then the file handler for 32-bit, and another 32-bit spatial code. Okay, and every user. Okay. Because in the beginning of this, the purpose of this app is used for university, for CME, okay, inside its university and all these related research institutes, okay, and so they assume every user has an account, and each user account will give a unique volume number. Say, so those users' files. They are created under the same volume, okay, and so on. And of course, a system will have a system's volume, okay, and so on. And every user will have 32 bits of the number of files, okay. And this 32-bit number of other, usually this can be used as a Boolean number or whatever other purpose, okay. And files are grouped into volumes for each location and movement. So when you try to move a file, you cannot move individual file from one server to another. You move the whole volume. That means because each user has associated with to a particular volume. So that means when you move a whole volume from one server to another, all the file associated with that particular user will move to the others also. Okay. So every user usually has a separate volume associated. User see the files by this page name hierarchy. Okay. But FS, Venus, and Vice, they use this FID to communicate between this Venus and Vice. Okay. And they also they only accept requests in these terms of FIDs. Yeah. That's file servers they only do. So Venus need to translate this page name into FIDs. And again, this translation is step-by-step lookup, okay, to attempt the information from associated device servers. Okay. So here is a system code, file system code in FS. Okay. You will see that the user uses this system and then go to the Unix kernel. Unix kernel may be modified. So some of them will pass back to the Venus. Venus will look at its local cache. If in there, then we'll access. If not, we'll translate this page name into FID, and then look up this mapping table. Every client has a configuration table, and this configuration will be sitting in shared namespace and system volumes, so that they all know for which file, which particular volume are managed by which file server, and so on. So they will send the request to the designated Venus project, and then they get back this particular files. Okay. So when you try to open a file with a mode, this request will go to the Unix kernel, and Unix kernel find out it is a file in the shared file space. Okay, because again it depends on this file hierarchy. So Unix file system they use this page name to look up, and then find out it's in the shared space. So we will pass the request to Venus. Venus will check, see there's a valid cache in its local cache. If it's in there or it's there but it's embedded, then you will send a request to server. Okay, which hold that particular file, and this server will send back the file with here we call it callback promise. That means it's an indication. Okay, and later they can use this to inform the client. Okay, because the FS is a stable server implementation, so their cache invalidation or cache update policy in general is initiated by the server. Okay, by using this callback promise. Okay, they send this one back to the Venus, and Venus will hold this whole file in its local cache, and then open this send back this cache file name to the Unix open system calls. Okay, and the Unix open this file and send back the file descriptor. And for subsequent read, okay, it's similar to the Unix file. You give the file descriptor with buffer, and then they perform normal operation. Okay, without bother this FS at all, and write. Okay, eventually it close this file, and then this close will be also intercept to the Venus. And Venus will look at, okay, this file is in the cache, and to see it's 30 or not. Okay, if it is 30, then you send back the whole content back to the corresponding Vice server. Okay, and replace. And this Vice server will send a callback promise to all the client which has original cache. Tell them there's a new version of this particular files. Okay. So this promise will embed those caged file. So the cage consistency management in here is when Vice supply a copy of file to Venus, you also provide a callback promise. Okay? And this callback promise is it's just a token. Okay? You guarantee that later they will notify the Venus when the file has been updated. Okay? The purpose for that is doing this. And so the Venus will store this and make its file become ready, okay, or cancelled. Depends on this promise, the state of this promise. And when some bytes server perform a request to update a file, okay, so it receives an update, okay, from some Venus. Then after this update, it will notify all the Venus who have been issued this callback promise. Okay. And this callback just is a procedural call from a Vice to a Venus. Okay. So the reason we call it callback, that means this is a call, the procedural call entry provided by Venus to Vice. Okay. So whenever you send a request from a Venus to Vice to ask a copy of a particular file, you also provide an entry, callback entry, and let the Vice know how to inform this Venus when the status changes. Okay. And this initially is ready, and when someone updates, then you will send out the cancelled callback state. So all these Venus receive, they will set the S token to be cancelled. Okay. That means its local cache is not up to date. Okay. And so later when the Venus handle an open call, you will check the cache. If the cache is there, but the promise is not ready, it's cancelled, that means you need to retrieve the new version. Okay. If the cache is the state of is ready, then you can use your local version. Okay. And so by using this, if a client machine crash and restart, okay, it's Venus must ensure all these callback are still ready. Okay, so when the client host recovery from failure, okay, because this cache state are kept in Venus, okay, database. So the first thing is to validate all these local caches are still ready. Okay, if not, then they need to send a request to the server, okay, to get the up-to-date version. Okay. And again, they have some similar mechanism as NFS. You have a freshness interval used to whenever you open the file, okay, you check this freshness interval. Okay, if the time from the server last communicate with the server is less than this, then you assume the file is still fresh, is still valid. Okay. Some API only a subset of this Vice server provided us something like the fetch. That means you try to get this content of this ID with corresponding attributes. Okay, because we don't have here. You didn't specify the number of bytes or whatever, because it is a whole file service. Okay, whenever you fetch the whole file. Okay, and store, you send back the whole file, update the content of the whole file. So you only use FID and the whole data. Okay, create means create a new file, okay, with and they will get back NFID. Remove the file. Okay, set lock. Okay, because well, to provide right consistency. So if several clients try to open a write to a particular file simultaneously, then sometimes you need to make sure that in any time instance, only one particular client can access, can do the update. Okay, if the application require that, then you need to lock the file. Okay, so the other clients cannot open for write for that. Depends on the application. So if you want to set the lock or not, okay, before you doing the write. Okay, that depends on application. If the application, if you already know only one user will doing the write, the other reader only doing the read access, then you don't need to use select in your application. If for some reason, okay, this particular file, you know that it's possible several writer may exist, then in your application you need to use this lock to enforce this consistency. Okay. Otherwise, so this in general it depends on the application. Okay, so user should know that because only user know how your application will be used. Okay, and so this is FS provide this set lock operation, but and release lock associated, but it's not necessary to need to be used for every application. So it depends on the application. Okay, and remove callback and break callback. That means it involve as a file. Okay, and break is a callback sent from a bytes to a VNAS. Okay, so you have these two different callback. Remove callback is sent from the VNAS to bytes. Okay, and break means the bytes sent back to the VNAS. Tell them this current file need to be embedded, be cancelled. Okay. After this simple file structure and the modern distributed file system, modern means after 1990 or in the beginning of the 2000, okay, they have because the storage, the technology development, so the performance of the network and the cost of the storage, the reason for that. So this structure was proposed. Okay, that means you have a directory service become called metadata server, and free file server is still there. Okay, and client module is still there, but you can see that to provide more reliable scalability and availability and fault tolerance. So this metadata server usually has multiple copies and running in multiple hosts. And file server also, they have multiple copies running in multiple hosts as well. Okay, so each client computer, they all have client module. And this client module, when for the control purpose, they will communicate with metadata server. For data access, they will communicate with the file server. And again, most implementation, these two are separated, implemented, and managed by different hosts as well. So metadata server, they may become a client of free file server as well. Okay, so that's the most modern distributed file system. Their architecture are more likely to do something like this. Okay. And here we'll discuss two of this file system. The first one we call is the more very commonly used. Okay, we call it Hadoop distributed file system. Okay. Here they have two. The name node is the implementation of the metadata server. Okay. And data node is the implementation of the file servers. Okay. Then all the client, they have a client module in there. Okay. So for metadata application, they send to the name server. Okay. Inside the name server, they maintain this metadata information. Okay. Data will see what information are the metadata. Okay. And for actual data rewrite, they communicate with these data nodes. And in this Hadoop file systems, every file is stored, partitioned into blocks, and each block are individually allocated into data nodes. Okay, so inside data node, they handle blocks instead of file. Okay, because a file may have, for example, a file has 3 blocks. Then these 3 blocks will be individually assigned maybe into 3 different data nodes. Okay, so from the file servers, this free file server, this free file server module, they only know the block. Okay, they don't know the whole file. Okay. Only the metadata server knows each file contain 3 blocks, and the first block is in which data node, second block is in which data node, and so on. And this information are kept in metadata server. Okay. And for the data node, they will handle this data access for a particular blocks. Okay. So the architecture for this is it's a master slave architecture. So metadata server acts as a master. Okay, the data nodes, this name node is a master. Data nodes are slaves. Okay, so file system namespace management by the name nodes. Name to file mapping, they are, for example, open, close, and renaming. This are all handled by name node. Data blocks allocation and deallocation are also handled by name node. Data nodes acting as a slaves, they only handle this data blocks management. Okay? They're doing the block creation, deletion, replication request for name node, and doing the data block service. They provide operation for read-write a particular data block. Okay, these are service to name node. These are service to client. Okay, so data node provide 2 kinds of service. This set of API for the name nodes. These are for the normal clients. So files in Hadoop file system, they are stored is treated as a sequence of blocks. All blocks except the last block are equal size. Okay. And file configuration parameter, each file will have this parameter. So for example, you can set the block size, what is the block, okay, and replication factor. Each block can set how much replication needed. For example, you can set the first block need to have 3 replication, second block need to have 2 replication, and so on. Okay, so every block can have different replication factors. It depends on your requirements. Okay, and blocks of the same file are allocated separate. Okay, so they don't need to be allocated into the same data node. They can be in different data nodes and can have different replication factors as well. All files are write once only. Okay, and can only be written by one writer at a time. Okay? And also all writes are appended to the end of the file. Okay? So it's a append only update semantic we're talking about, okay, before. Okay, you can only write once, and then you cannot do any modification after you write. You can only append new data into the end of the file. Okay, and so on. So here, the block replication in Hadoop is something like this. Whenever you call the name node, you tell, so I need to create a file with a file name, and then you give the number of replicas with block ID, something like this. Okay. For example, these are two a specification for the blocks. For example, you give the page name of this one, data, and for this file, you have a two replication specification. Part 0 is for block 2 for replication factor of 2, and for block number 1 and 3. And this another replication specification with replication factor set to 3 for block 2, 4, 3. So these two line of configuration represent, say, tell the namespace, the name node that this particular file slash users slash sample slash data, okay, will have 5 blocks, okay, and the block 1 and 3 need to be set to 2 replications, and block 2, 4, 5 require 3 replications, okay. So eventually, this file have 5 blocks. They may assign something like this, okay. The block 1 in here and in here, because block 1 need to have 2 replications. So you need to have 2 copies of block 1 and 2 copies of block 3, okay, and 3 copies for block 2, 3 copies for block 4, and 3 copies for block 5. Okay, so eventually the allocation may look something like this, okay. The policy for block assignment, okay, maybe have this 4 kind of allocation policy, okay, can be used for the name node, okay. The simple policy is that all replicas are in different racks, okay. Hadoop usually assume that those disk data nodes, they are arranged in racks, okay, as a cabinet, okay. So you may have several cabinets, and each cabinet has different racks, okay, and each rack have a lot of several data nodes, okay, and so on. So they will allocate for reliability reasons, okay. So different replicas are all assigned into different racks, okay, to assure that they will not be affected by the same power crash or power failure, for example. So in the same rack, usually you may have several nodes, but they are handled by the same power supply, okay, that's all. Okay. The disadvantage is that the cost for the write, because they are in different racks, okay, so they need to go through different set of region of the segment of the network and so on. Okay. And so the second policy, usually you call it rack locality awareness policy. Okay. Usually the first replica is stored in the nearest data node from the requester. Usually it means it depends on the creator of this, okay, data node, these blocks, okay. And so the data node will create it in new is one host, okay. Usually maybe in the same rack, okay, or at least in the same cabinet, okay, you select one. And then second replica is also placed in the same rack as the first replica, but in different nodes, okay. A rack may have different data nodes, so you select replica, first replica in the particular rack, and then you select you store the second replica in the same rack but a different data nodes. All the other replicas are placed randomly, okay, outside this rack. Okay. The purpose for this is that you make you assume this power line failure and network segment failure is very, the possibility to happen is very rare. So you make this performance is much important. So you make this first two rack two replica, they are in the same place. Okay. The other policy, they may have a different kind of concerns. Okay, so for example, a disk, a data node, if its disk is highly utilized, okay, then whenever you try to create a new block, you will not try to assign new block to those already highly used data nodes. Okay, that's some rule of thumb. Okay, and some nodes, if their workload is already high, then you try to avoid to assign new blocks to those nodes. Okay, highly utilized and high workload are different. Okay, from different point of view. Okay, highly utilized means their disk is almost full. High workload means those data blocks occupied, handled by this data node are highly used. Okay, so the traffic is very high. Okay, this is the utilization. The disk is highly utilized. Okay, so and another rule of thumb is that the fast and slow nodes, because every data node they may have different performance speed. So for fast nodes, they usually treat them different to the slow nodes. Okay, in general, a node has high frequency or less latency. Then you may assign more data block into there. For a node which is slower, then you should assign proportionally less block to there. Okay. And also we need to consider some situation where we need to do replication. That means if the replication factor has been changed, then you need to do something about that. Okay. For example, a data node may become unavailable. Okay. For example, crash or whatever reason. Then those data blocks maintained by this data node it will become unavailable. Okay. So to make this replication factor back to the original requirement, then you need to reassign some data block to other data nodes. So this is a re-replication requirement. And also maybe it's not the whole data node become unavailable. Maybe just a replica become corrupt. Okay, because the disk failed. Okay, so some part of the disk, particularly associated with a particular data block, failed, crashed. Then you need to do something about that. Okay, or hard disk failed. Okay, the data node failed. In here, become unavailable, maybe the network failed. Okay, and here is the node failed. This is associated with the disk failed. So you may have different different situations for this. Okay, but anyway, you may need to do some re-replication. Okay, and also another situation is that when user increase the replication factor. So for example, in the beginning you said this block 1 is only need 2 copies, and later you find out the block 1 used very frequently. Then you expect, then you may change this block 1, the replication factor from 2 to 3. It depends on your long-term usage. So after this change, the metadata and the name node need to be assign a new block into into some data nodes. Okay. To manage the metadata, okay, the name node maintains these 2 log files. The first, this one is file system image. That's the whole file system as a checkpoint. You checkpoint the whole file system, all the metadata of the whole file system. Okay, so it contains entire file systems, namespace, mapping, information, and so on. Okay, and this checkpoint is a whole checkpoint periodically. Okay, they check the whole file system image. So it's called fire system image. Okay. And then after a checkpoint is made, okay, before the next checkpoint, all this updated information, the request, they will store in this AD log. You create another file to record those update operations. Okay, so record every change made to the file system since the last checkpoint. Okay, so use this tool. When the name node crash, you will be able to recover from other host. So for example, you have a host running the name node, and these files are maintained in the disk. Okay, and this disk is shared by another host. In general, you can do that because right now there's a lot of disk device. They are network enabled disk device, so they can be attached to multiple hosts. Okay. So when the host crashed, but the data is still there, you can launch the name node in another host, and then use this and this to recreate the namespace, okay, or the metadata in another name node. Okay, and then after that, all the requests for the metadata operation we are sent to the new name node and so on. Okay, so if the name node fails, a new name node can be launched. Okay, with the last checkpoint, and then make update in this AD log. So in a normal situation, the file system image, okay, the whole metadata are maintained in the memory of the name node. Okay, so it's the memory register. Okay, the metadata are in the memory of the name node, and with a checkpoint in disk and AD log in disk. Okay, and this disk are assumed number of times, so we're not affected by crash, no crash, and it may be accessible by other hosts as well. Okay, so you have this assumption. So file creation scenario in Hadoop usually look like this. A file created request by a client. Okay, they in general they only create a file in the beginning. It's created in the client host until the first block are fulfilled. Then you ask the name node to create the file and assign corresponding data block to data node. Then this client host will send the whole block to those allocated data nodes. Okay. So in general, a file first created in client's local disk, and then you do some write operation until the whole block are full. Okay. And the default data block is 64 megabyte. Okay. Okay, we will stop here and then we'll continue in the next week.
你来说一下，跟老师讲一下事情。
哦，好，那好。